Hello, students. So we're continuing with the gas laws chapter, and what we're going to be talking about is Dalton's law of partial pressures, and then we're going to get into kinetic molecular theory, and after that, what real gases are like and how they differ from the ideal or perfect gas. So Dalton's law of partial pressures, what it tells us is basically if you have a mixture of gases, then the total pressure in that container is the sum of those individual pressures of each gas. So sometimes you have a container with a pure gas, say it's just pure oxygen, nothing else in there, then the total pressure of that container is due to just the pressure of the oxygen, those particles hitting the walls of the container, creating that pressure. However, if you have two or more gases, then the total pressure is just the sum of those. So let me just show you how that's kind of written out. P total, P is for pressure, so the total pressure is the pressure of gas A plus the pressure of gas B plus as many gases as are present plus pressure of B, it's C, D, etc. So let me just show you this visually. Say you have a container with just one gas. We'll call this gas A. I'm going to tell you, okay, these 5 particles say impart 1 atm, a pressure of 1 atm. Gas B here, the green ones, there's more in there, and it ends up having a pressure of 2 atm. If you combine those, then in that same space, you have now 5 plus 10 particles, you have 15 particles, there's a higher pressure, and the pressure is just the sum of the pressure of each of those. So if you know the individual pressures, you can add them up. 1 atm plus 2 atm gives the total pressure of 3 atm. So the other thing that I want to mention is that the total pressure is dependent on the amount of gas in there. So if you take a look here, the partial pressure of a gas is actually proportional to what's called its mole fraction. So the mole fraction is basically written out this way, but just let me just say this in words. It's the number of moles of that gas out of the total moles in the container. So what this is saying is the partial pressure of gas A here, let's say we didn't know it, we wanted to find it. What we can do is find out how much, what fraction of the blue gas particles, gas A, is out of the total gas particles. And then if you know the total pressure here, what you can see is that the pressure of A is its mole fraction, the fraction of how much is in there, mole-wise, times the total pressure. So let's work through this. We have the same containers of A and B. And what we do is we mix them and we have both A and B together. Let's say we have 5 particles of A, and if you count it up, you have 10 particles of B. So there's more B than A. So B is actually going to be 2/3 of the mixture. A is going to be 1/3. And I just did that by looking at mole fraction. There were 5 A's out of the total 5 plus 10. So 5 out of 15 is 1/3, so it's 1/3. So the mole fraction of A is 1/3. You could have just looked at that visually. It's about 1/3 of that mixture. So if you know the total pressure, then you can conclude that the pressure of gas A, if its mole fraction is 1/3, then it's 1/3 of the total pressure. So 1/3 of the given 3 atmospheres for the total pressure is just 1 atm. So just to state that out, since gas A makes up 1/3 of the total gas particles, its pressure, its partial pressure, which we call PA, is 1/3 the total pressure. So depending on what you're given, maybe you're given all the partial pressure, then you're asked to find the total pressure. You just add them up and you get that total pressure. But what if you're given the total pressure and you're given maybe the amounts of A and B? Then you can find the moles of those, find the mole fraction of the one you're interested in, and just multiply that by the total pressure. Okay, next is kinetic molecular theory. So these are basically a list of assumptions that are made that help us arrive at the ideal gas law, where we consider that a gas is ideal or perfect. So here are some assumptions: that the gas particles are very, very tiny and the volume is negligible. The reality is that there are some gases that are large. Maybe the atom size is large, maybe there are a lot of atoms connected together and the molecule itself is large, but either way, the volume for some real gases are large. We'll get to some non-ideal gases in a moment. We assume that the motion is random, that these particles are just bouncing around on all hitting the sides of the container at random. But we know from our previous chapters that there is some intermolecular force between particles. Sometimes these can be very, very strong, like hydrogen bonding forces, or it could be weak, more the London dispersion forces. So we're assuming that there is no interparticle attraction. This plays a role in the pressure. If there is interparticle attraction, then they're connected more with each other versus hitting the walls of the container. That affects the pressure. We assume that the collisions are elastic, meaning kinetic energy is constant, that energy is not lost when you collide with another particle, and that the average kinetic energy is proportional to the temperature. Okay, what comes out of this in terms of the kinetic energy and relating that to the actual particle, the molecule? Basically, you can come up with, through manipulation of some equations, you can come up with an equation for the average speed of a gas particle. So the average speed, U, here, is the square root of 3RT, so we have temperature, divided by molar mass. Because of the units involved here, the R value is not our typical R value units. So our R value is different. It's 8.314 joules per Kelvin mole. And the reason is we're going to be working in joule units, which can translate to kilograms, and thus molar masses in kilograms. I do not have you guys use this equation for any calculations. If for some reason it shows up, you would be given the equation and the constant to use. But what I really want you to get out of this is just think about these variables, temperature and molar mass. How does changing the temperature or molar mass affect the speed of a particle? So again, these are particles moving around at random. If you increase the temperature, what are you doing? You're increasing the energy of that system. So there's more energy, the speed will increase. What about molar mass, which is inherent of a molecule? If the molar mass is really, really high, if this is a large number, look, it's in the denominator. So that decreases the speed. Heavier gas particles will have a lower average speed. Hopefully that makes sense to you, thinking about trying to move a heavy bowling ball versus a lighter ping pong ball. If you give each the same energy and push them, the one that's lighter is going to go faster. Let's look at a correlation with average speed and temperature. So what I have here on my y-axis is the speed of nitrogen molecules. So this whole chart here is about nitrogen N2 molecules, and this is the relative number of molecules with a certain speed, increasing as you go up. On the x-axis is the speed in meters per second. So each of these colored curves corresponds to a different temperature. The blue is the lowest temperature of 273 Kelvin, which is 0 degrees C. The most probable speed is maybe around 600 meters per second. Notice you do have a bell distribution here. If we increase the temperature 1,000 degrees, we get this brown curve, a greater distribution of speeds. Some can go really, really fast at this higher temperature, and the most probable speed is close to 1,000. So the main point here is as you increase the temperature, you increase the most probable speed, the average speed. The red is at 2,000 degrees C or 2273 Kelvin, and you have a greater distribution, and the most probable speed is maybe around 1,400. Okay. Another concept I want to touch upon is the effects of pressure. Why the effects on pressure with different gases? Why don't heavier gases exert more pressure? The reason is, remember that pressure is hitting the sides of the container. And we just talked about that average speed. Even if one is heavier, for example, O2, which has a molar mass of 32, versus hydrogen, which has a molar mass of 2, even though it's heavier and will move slower, they still have this similar kinetic energy hitting the sides of the container. So they'll be heavier, but they'll move slower and hit it at a slower speed, versus the lighter ones. Those will move faster, but it is, sorry, they are lighter. Okay, the last topic in this section is talking about real gases. When gas molecules are not perfect, they're not these ideal gases, which is a reality, right? There are interparticle attractions, there is a certain volume that a gas makes up. So if there is an interparticle attraction, basically intermolecular forces present, gases will exert lower pressure on the walls of the container. The reason is they're not free to bounce and hit and collide with the walls of the container. There's something holding them back a little bit because they're interacting more with each other. So consider water versus hydrogen, H2. Water has hydrogen bonding forces that'll make them interact a little bit more with each other, not be so free to hit the walls of the container as much as the nonpolar H2 molecule that only has London dispersion forces. So in this case, in terms of the PV equals nRT, that pressure is lowered. So if you wanted to maintain that relationship of PV equals nRT, you would need to adjust the pressure up. In terms of particle volume, if a gas makes up most of the container and there's effectively less container volume, remember the assumption that we assume that these gas particles or molecules are tiny relative to the volume, then we would need to adjust the volume down in that case. So let's look at how the ideal gas law can be modified. If you adjust for pressure and volume, the ideal gas law becomes this, which is not an equation I have you guys use to plug in numbers or anything like this. I just want you to understand that there are adjustments for real gases for pressure and volume. This term here has a constant A. This term here for volume has a constant B. These are constants that are very specific to each gas based on their own intermolecular forces and their volumes. They're determined experimentally, and you can look them up in a reference book or a table. So let me just show you an example. How about the water example that I gave? Water has hydrogen bond forces, so its A value will be much higher than hydrogen, which doesn't have much intermolecular forces because it only has dispersion. So look at the A value of water is very high. It's 5.5 versus 0.24 for hydrogen. Their volumes don't differ much, so we have a similar B value. Again, this is due to the hydrogen bonding of water. Something that might have a high B value of say 0.13 versus 0.03 is observed for this silane here with 3 chlorines and a fluorine attached. The reason is this is a much greater, bigger gas with a higher volume. So it'll take up more space in that container. Okay, this is where I'm going to end, and we'll continue more with other videos.